based on this, right? Because this is that, yeah, for a given psi. So that's where this angular bracket notation came from. That's its origin for the expectation value of observable A, the physical quantity A, whatever it is. Okay, so yeah, it's just sayings here. So that's where this notation, angular bracket notation, came from. Right. Now let's. Now this is for a general wave function. You know, general wave function usually means a superposition, because that's the most general form. If it's not a superposition, in other words, it's just, let's say, an eigenstate. So let's say this general wave function here is a special case where it's just an eigenfunction. It's one of the eigenfunctions of this operator, let's say. Okay. Well, then, in that case, in that special case, when your general wave function is now an eigenfunction, what is the expectation value for that observable with the corresponding Hermitian operator A hat? Right? Well, you instead of putting psi, you put psi n now, the eigenfunction. Now, now you can operate on, you can use this operator to operate on the left or on the right. You know, it doesn't matter. It's Hermitian, right? That's the whole point of using this notation now. We've got a sort of mirror symmetry with these two bars. That's why we do it that way, and it sort of reminds us of this symmetry property of A hat. Because of its hermeticity, because it's Hermitian. Okay. Well, let's say we operate on the right-hand side. So A psi n, with this ket here, will just be lambda, which is real, right? So it'll just be lambda n psi n. It's just the eigenequation, right? So and here we have the two same eigenfunctions. Now these eigenfunctions are orthonormal. Remember. So this is just 1, and we're just left with lambda n. So the expectation value for your observable A will just be one of the eigenvalues. It'll be one of the allowed measured values corresponding to the eigenstate psi n. Right? It just falls out of the mathematics. But physically, if your quantum system was an eigenstate, one of these eigenstates, psi n, with a corresponding eigenvalue lambda n, then you could do the measurement umpteen times, and you'd always get that value. So if it's always that value, of course the expectation value will be the same, right? It's common sense. Okay, and that's what I'm saying here. So you'll always, if you're in that state, that eigenstate, you'll always get that measurement result when you do the measurement, right? Okay, now the last little bit for this session, as I was saying a bit earlier, we're heading more and more towards chapter 7. Which is also a very long chapter. It's 20 pages. It's the second longest in the text, with a lot of theory. The standard is lifting a bit, as you'll see in chapter 7. But our operators then are not differential operators so much. They're more, well, they are to some extent, but the emphasis becomes more and more on matrices. So we'll be using Hermitian matrices. So so there's a little bit of discussion here on how you go about using a Hermitian matrix as an operator. Well, I'll draw it in. Imagine here's your square matrix. And represent a state, an eigenstate, well, a state, it's just a general state, as a column vector, right, of this form here. So this is your Hermitian matrix A, That's a square matrix, right? So this will be of the form n by n matrix. Now, as a column matrix, so n rows, one column, so it'll be n by 1. And the result, when you multiply a column matrix by a square matrix, n by n, you will get the resulting matrix also n by 1. So you can think of now an operator changes the state of a function into another function in general, right? That's sort of the way you look on what an operator is in the context of quantum mechanics. So if your function now, a wave equation, a state, look upon a quantum state as a vector now, and the vector is now a column vector, an n row, n by 1, n rows, one column, so it's a column vector. And if you multiply that on the left by an n by n Hermitian matrix, you'll get another column vector n by 1. Okay, so you can look upon this matrix here as an operator which changes this state, this state vector, into another state vector. Right? So this thing changes the state vector into another state vector. So you can look on this matrix as an operator. Right? That's what operators do. Change state vectors into other state vectors. That's what this matrix is doing. Okay. Now the algebras, the two algebras, are effectively the same. Whether you're talking in terms of matrices like this or brackets, you can switch back and forth. They're equivalent, but it's just more convenient when talking in general, when talking about angular momentum and so on, to use Hermitian matrices. Okay? Right, and I mentioned this a bit before, but historically, this matrix approach was used first in the major revolution in the 20s, when Heisenberg, the real father of modern quantum mechanics, his conception was in terms of matrices, but he didn't know what matrices were at the time. He just sort of invented it in a sense. And it wasn't until his supervisor, Born, the famous Born of probability distribution, that Born, noticed that what Heisenberg was doing was manipulating matrices, so he called it matrix mechanics. That Heisenberg didn't like very much, the term. So anyway, Heisenberg used this matrix approach for his version of quantum mechanics, and I think about a year later, then Schrödinger came along in Austria, based in Vienna, and invented his wave mechanics. So for a while there was a bit of controversy in which of these two pictures, these two ways of looking at quantum mechanics, was more valid, until Schrödinger himself proved that these two, the matrix mechanics, using matrices, matrix operators, and wave mechanics using differential equations and wave equations and so on, were in fact equivalent. Okay, but as said several times, when we come to chapter 7 and talk about angular momentum, it's just easier to use the Heisenberg approach, using matrix mechanics, matrix operators, and the like.